got the 5-piece band.
It's my favorite lab, actually, that we had last semester.
Okay, so I know that we still need combustion analysis, but we're coming back to that part 3. We will. And I like how I'm going to do this because it just is good. We're going to end up talking about titrations, which is solutions, stoichiometry, and then we're going to kind of come back to combustion analysis, which reminds you what we talked about the first part of Unit 2. I like it. So, solution concentrations. So we talked when you classify matter, you can say it's either a pure substance or a mixture, and if it's a mixture, it can be either homogeneous or heterogeneous. So actually, solutions are a homogeneous mixture. Okay, solutions are just a homogeneous mixture. There are a lot of S's in solutions. I find it irritating. Okay, so solutions tend to have the solute. The solute is there in lesser amount, dissolved in a solvent. So I draw pictures, sometimes. And so here's my picture of making a solution. Where should I do it? I guess up here in this corner. Okay, where there's my beaker, obviously. Okay, the liquid down here that's in a lot is called the solvent. It doesn't have to be a liquid solution, but liquid solutions are great. And then you sprinkle in a small amount of solute. Solute, okay? Together, the solvent plus the solute is the solution. Too many S's, okay? So like this says, you can have more than one solute dissolved in a solvent. And an example of a solid solution, I don't know if I mentioned this before, but actually stainless steel, okay? Stainless steel, any sort of brass sort of alloy, actually what it is basically atoms of different elements that are frozen together in a homogeneous mixture. So it's like a solid solution. So, an important type of solution called an aqueous solution, the AQ means basically you have some sort of ions running around there in water. So an aqueous solution has water as the solvent. If you've ever heard the phrase, water is the universal solvent, it's a pretty darn good solvent. A lot of things dissolve in water. Not everything, though, obviously. So we need to talk about how do you say how concentrated is the solute in your solution. How concentrated is the solute in your solution? We're going to focus on basically amount of solute per given amount of solution. Okay, in Chem 1. In Chem 2, we're going to switch gears, and actually we're going to revisit solution concentration and talk about solute per amount of solvent with a V. Okay, so 2 ways I want to talk about solution concentration, and they both deal with amount of solute per amount of solution, which is the solute plus the solvent. Too many S's. Okay, so just generic terms, we could say that something is concentrated. That means it has a lot of solute per given amount of solution. If a solution is dilute, that means it's the amount of solute per amount of solution is kind of sparse. Okay, so these are the 2 types of ways, and actually there's a third way we've already talked about. How do you say how concentrated the solute is in solution? One is grams of solute per liter of solution. And I'm all about this, right, where between my hands is a divisor. So grams of solute per liter of solution looks like this. Anytime you see the word per, think divisor. So this would be G solute per L solution. And my abbreviation for solution is SOL apostrophe N. Isn't that clever? Okay, so that's one way of saying how concentrated your solute is in your solution. The other one, I'm sure for some of you it's been maybe longer than others, but you probably have run into the term molarity. Molarity is basically saying how concentrated a solution is. Molarity is moles of solute per liter of solution. Moles of solute, like hee-haw, per liter of solution. But you guys don't even know what that is. Stand up in a cornfield and do this. Okay, moles of solute per liter of solution. So, grams of solute per liter of solution. So honestly, if you're a picture or a visual sort of person, basically both of these are describing You know, here's your beaker. Okay, you can tell it's a fluid because you see little waves up there. This is your solution. If we make this 1.00 liters of solution, you know, actually we can use that as our basis sometimes. We can already say, well, you know, X grams of solute in that liter of solution, or Y moles of solute in that liter of solution. That's kind of what we've got going on here. How concentrated is the solution in terms of amount of solute, whether that amount is in grams or moles per given amount of solution. And we're going to go with volume of solution in this case. So that brings a good point. Since we're going with volume, in this case liter of solution for both of these, one thing about volume is it's kind of a moving target with regard to temperature. We talked about the density of water and the fact that water actually becomes more and more dense as you approach its freezing point. And all liquids, basically, as long as they stay a liquid, will go from being kind of fluffy. If you cool it down, that liquid will occupy a smaller volume. Okay, so honestly, grams per liter of solution and moles per liter of solution are both a moving target in a sense with regard to temperature. When we work with, I think I said this before maybe, but when we work with like glassware designed to measure volumes of liquid in the lab, the glassware will say at what temperature that it's calibrated to, usually 20 degrees Celsius. So they are temperature dependent. All right, so let's do a problem. And kind of for reasons, we're kind of do two problems with the same scenario. I'll go ahead and draw a picture here. Pictures are optional. You know, here's one of my famous beakers. All right, it says you're dissolving 32.3 grams of sucrose, 32.3 grams of sucrose, and your final solution volume is 225 milliliters of solution. You know, sometimes a picture in these cases to me just can kind of say, oh, I can see how to work that problem. Okay. So we're supposed to say what is the concentration, question mark, concentration, in grams of sucrose per liter of solution. That's our target, right? And so you'd be like, well, I have grams and I have grams of sucrose in milliliters of solution. It seems kind of straightforward, and it is, okay? So to work this, what I would do is simply take the grams of the solute, which is 32.3 grams. You could spell out sucrose if you wanted to, instead of C12H22O11. If you abbreviate it like SUC or something like that, a good way to would be to say as you know, the top part of your problem, divided by the solution volume, which is 225 milliliters. So right off the bat, can you see units we have are grams per milliliter? Not quite grams per liter, but we're close. So we can introduce one more term to what I say, fix the denominator. So it'll be 1,000 milliliters over 1 liter, be on the next term. Now units of milliliters have canceled. We have units of grams of sucrose per liter of solution, and we're done. Looks like we're allowed 3 significant figures. Calculators ready? So I got 144 grams of sucrose per liter of solution. Now, grams of sucrose per liter of solution. Now, that's like the sort of the unpacked way to write it. Kind of the packed up way to write it, way you usually see it, is simply this. 144 G as in grams per liter. G slash capital L. So that's grams of solute per liter of solution. And then go ahead and say what the solute is. So 144 grams per liter of sucrose. C12H22O11. Not too bad. Well, let's look at the same solution and now say what is the molarity of the sucrose. Instead of grams per liter, we want moles per liter. Same problem. What is the moles of solute per liter of solution in the previous problem? So we could actually, we're going to piggyback on our 144. 144 grams sucrose per 1 liter solution. Okay. Second question mark. Moles sucrose per liter solution. You know, we've been talking about the factor label method of working problems. Do you see basically where all I have to do is convert or change grams of sucrose to moles of sucrose in my 144, and then I have moles of sucrose per liter of solution. So we're going to piggyback right now. Alternatively, I'll say alternatively in here in a minute. So in order to go from grams, I wish I had another color. All I've got to have is black up here right now. In order to go from grams to moles, we need to use the molar mass of C12H11, excuse me, C12H22O11. So I graded some homework, and not everybody's showing your molar masses. You have to show this, no matter if you've got it right. Okay. So we're going to take 12 for carbon, 12 times 12.01, plus 22 times 1.008 for hydrogen, plus 11 times 16.00 for oxygen. And that's a honkin' heavy molecule. 342.30 grams per mole. That's going to be our ticket to get from grams to moles, the molar mass. So here we go. Like I said, if we piggyback on the concentration we already found, 144 grams of sucrose per 1 liter of solution. Now I want grams to cancel. I want to be left with moles in the top. So I'm going to use the flipped version of the molar mass. 1 mole of sucrose per 342.30 grams. This is another example of, do you have to be explicit? Do you have to say of sucrose? Well, probably not, since you only have one species you're interested in. So it looks like the grams cancel. We're left with moles, moles over liters, moles of sucrose over liters of solution. We're done. Round to 3 significant figures. I get 0.419 moles of sucrose per liter of solution, and 1.49 moles per liter of solution. I say that, like the C12H22O11, or the word sucrose, that's optional, but honestly, probably the term solution is not optional, because actually here in this unit we're going to be talking about volumes, different volumes of different things. So I think you should be explicit. Regard to that. Okay, so you got what? Different?
I got 0.421.
Ah, I must have used an unrounded number. Let's see. I believe you.
I think you don't round if you don't use the 144.
Okay, thanks. If you use an unrounded number instead of the 144, then you get this number.
Yeah.
Okay, thanks. Great. So I would take either number, and I would track it down. So I mentioned using kind of not piggybacking. Let's see if I can do that. If you weren't going to piggyback, can I do this? No, I can't. Huh. I can do that though. Okay. So if you weren't going to piggyback, it would look like this. And this is usually how I work this problem. To get molarity, to get moles per liter, I would put the grams, the 32.3 grams of sucrose, 32.3 grams of sucrose. Okay, I would probably put that over the solution volume, 225 milliliters solution. If my target is, question mark, moles of sucrose over liter of solution, if that's my target, notice I need to fix both my grams need to go to moles and my milliliters need to go liters. So whichever one you want to fix first, let's go ahead and fix the liters, the milliliters to liters first. 1,000 milliliters over 1 liter of solution. And then if we go ahead, and I'm running out of room, if we go ahead and use the flipped version of the molar mass, which was 342.30. Sucrose for 1 mole. Sucrose. Okay, that's like starting from scratch. Okay, so now you look at what cancels. Of course, units of grams of sucrose cancel, units of milliliters cancel, and then we're left with liters of solution in the denominator and moles of sucrose in the top. So that's how we do it from scratch. Okay. So instead of the whole 0.149 moles of sucrose per 1 liter of solution is kind of like it's ready to be used in a factor label problem. If you're writing a report and need to express solution concentration in terms of molarity, just use a capital M. Okay? In Chem 2, like I mentioned, we'll be talking about, dare I say, molality. And it differs only by, I don't know, not very many letters. And it differs only by the capitalized versus a lowercase m. So my point here is it's definitely an uppercase M for molarity. Cool. So this worked in my office. If you're asked to make a solution and you use, and it's hard to, the stuff doesn't want to dissolve, like some things dissolve right away and some solid solutes take a while to dissolve and you don't want to get carpal tunnel, okay? And you end up using a stir plate, make sure that you take the stir bar out after it's all dissolved and you bring it up to final dilution. Otherwise, basically, you have a stir bar down there that's messing up your volume. I've done that before. Another thing, and actually you guys are going to make your own solutions when you do, not this week, but next week's lab, you're going to make your own standard sodium hydroxide solutions. Once you dilute something up like that, you want to go ahead and mix it a few times. Because otherwise, if you take off the top, you know, you're basically taking off the least concentrated and most concentrated. So those are just a couple of things. Okay. But the other thing is this piece of glassware that's used is a volumetric flask. So not all glasswares are created equal with regard to being accurate, and so we kind of talked about that before too. So here's kind of a still image of doing the same thing, taking the solid solute in this case, and the caption of what's being done is down below here. One of the things with chemistry problems is reading a paragraph like this and saying, now what is that? Okay. So they're saying the goal is to prepare a 0.250 molar solution of that's potassium chromate, dichromate, potassium chromate. Okay, and so actually that's what this is, 0.250 molar K2CrO4. Okay, and it says 12.1 grams of solid solute are added. 12.1 grams, okay, and it's diluted to a final volume of 250 milliliters, okay. So now notice this piece of glassware, actually you know it to 4 significant figures, so that's kind of what we've been talking about. That's not a small thing. Oh, I guess it says 250 without the 0, but my bad. Okay. All right. So let's do a problem that's not quite as simple or straightforward. This actually is dealing with a hydrated salt. We talked about hydrated salts before. It's This is nickel 2 chloride, and it has 6 waters of hydration. So let's go ahead and start a little picture over here. I think this will work. Has 6 waters of hydration. Now the thing is, once you dissolve the hydrated salt in water, guess what those waters of hydration do? Beep, they just blend in with the background. Okay? So that's one of the things that you have to kind of consider as you work this problem. So here's a picture. I know what I was going to tell you. Okay? So the whole, we usually make solutions up in volumetric flasks, but beakers are easy for me to draw. So here we go. We are adding our solute, which is 8.320 grams of NiCl2.6H2O, nickel 2 hexahydrate. It goes on to say that we're going to go ahead and bring up a final volume. Okay, final volume, won't be in a beaker, probably be a volumetric flask, of 250.0 milliliters solution. That's our final solution volume. So we are supposed to, and I'll go ahead and tell you a couple of ways to do this, but our first goal is to come up with grams of the nickel 2 chloride, NiCl2, the stuff without the water, per liter of solution. And then secondly, we are supposed to come up with moles of NiCl2 per liter of solution. Okay, that's our goals. Sometimes it just, I don't know, it's stalling, right? You draw a picture, but sometimes, especially unpacking either what you have or your goal, units of your goal, I think can help. The problem with this problem, like I said, is the waters of hydration. So I'll kind of show you how one way to handle that. So you'll need the molar masses of everything. You guys already have the molar masses of everything?
Yeah.
Good, okay. So we have the molar masses of just the unhydrated salt, the molar mass of water, and the molar mass of the hydrated salt. Okay, so we can refer to this slide. So my first approach, actually, and this is fair game, is to look and say, I'm going to go for the moles of nickel 2 chloride per liter of solution first. You don't have to, but this is just what I'm going to do. Okay, I'm going to go ahead and just, I know. I'm going to first come up with the moles of nickel 2 chloride in that mass of hydrate. Okay, so I can recognize, first I'm going to go ahead and convert that to moles. I'm going to use the molar mass of the hydrated salt, the flipped version. Okay, 1 mole of nickel 2 NiCl2.6H2O per 237.69 grams of NiCl2.6H2O. So basically the molar mass of hexahydrate. Of course, that will give me moles of nickel 2 chloride dot hexahydrate. Then I need to recognize that for every 1 mole of that, 1 mole of the hydrated salt, I have 1 mole of the anhydrous. So I have 1 mole of nickel 2 chloride per 1 mole of NiCl2.6H2O. So honestly, doing it this way, do you see where, in the first case, we basically got from grams of the hexahydrate to moles of the hexahydrate, and then we got from moles of the hexahydrate to moles of the nickel 2 chloride. And I'm almost there, right? Nickel 2 chloride. I'm doing this one in steps. Actually, I'm going to resolve that, and I'm just going to divide by the solution volume. So rounding it to 4 sig figs, okay, looks like we have 0.03500 moles of just the pure nickel 2 chloride running around in there. 0.03500 moles. So then the last thing is to divide it by this volume and to clean it up from milliliters to liters. So here we go. That 0.03500 moles of NiCl2 divided by 250.0 milliliters of solution. I'm still, now I need to fix my denominator. I have units of milliliters, I need to get them units to liters, so I can do that with 1,000 milliliters of solution over 1 liter of solution. So now I have units of moles of NiCl2 per liter of solution, and we're done. Looks like I still am justified for significant figures. So I got 0.1400 moles NiCl2 per liter of solution. Then there at the bottom, the big M, we can just say simply 0.1400 molar NiCl2. And we're done. And then it's not too bad, since I have moles of NiCl2 per liter of solution, I can get to grams of NiCl2 per liter solution using the molar mass of NiCl2, which we had before. So if we piggyback to get A from B, okay, it looks like this, where we just introduce the molar mass of the NiCl2. So it would be the 0.1400 moles of NiCl2 over 1 liter times the molar mass of NiCl2, which is 129.59 grams of NiCl2 per 1 mole of NiCl2. So moles cancel, we're left with units of grams of NiCl2 per liter solution. Rounded to 4 significant figures again, I get 18.14 grams of NiCl2 per liter of solution. What I thought it was going to say is like this 18.14 G/L of NiCl2. And that's it. There's definitely more than one way to skin this cat. So this is kind of one where I just meet you on the other side. And like I said, if you're within a, few hundredths or, like, okay. Okay, so alternatively, you could go for A first. You could go for the grams of nickel 2 chloride per liter of solution, and this is one way to do that. If I simply go ahead and put the mass of the hydrate, 8.320 grams NiCl2.6H2O, over the volume of the solution, 250.0 milliliters. Then you see I got to get to the grams of nickel 2 chloride in that particular situation. Now, this ratio, actually, if you look back a few pages, if we consider 1 mole of the hydrated salt, you look back a few pages, this bottom down here is the molar mass of the hydrated salt. This right here in red is the mass per mole of the anhydrous salt. So these two are molar masses. And if you just consider 1 mole of the hexahydrate, you do indeed have 1 mole of the anhydrous. So these came from a few slides ago. Basically, it's a mass-to-mass ratio. But so if you're willing to buy that, which is totally cool, then grams of the hydrate cancel out with grams of the hydrate, and things are really looking good because you have units of grams of the nickel 2 chloride per milliliter of solution, unit-wise. And that's all we focus on is units. So all we got to do is finish up getting liters in the denominator with this term, 1,000 milliliters solution over 1 liter solution. Rounded to 4 significant figures. Okay, hopefully it will be what we got before. 18.14 grams of the pure nickel 2 chloride per liter of solution. And I'm sure there's more than one way to work this. But whatever way you work it, you have to show your work. Makes sense? It doesn't have to be the way I did it. Voila! All right. So just briefly, we'll take a look at these. It's kind of cool because I've come about a year ago. Last year, I started showing students the homework, and so now I don't have to do them right before class. I think, which would be nice. No offense. Okay, so it looks like this. Okay, so 33 and 34. So what are the molarities of A, B, and C? Okay, so probably not going to necessarily belabor any of this. Okay, so I went ahead and gave you some hints for A, B, and C. Some of them you need, probably don't need them much. The only catch I guess I would mention is C. C, basically, the solute is a liquid. C, actually, you're dissolving methanol, and I abbreviated it MEOH. So you're dissolving methanol, 125.0 milliliters of methanol for a total solution volume of 15.0 liters. So basically, you need to get moles of methanol out of that volume of methanol. Luckily, they give you the density of methanol. So basically, my hint here was to use the volume, that 125 milliliters, and the density, remember that's rho, to get to mass, and then use the molar mass of methanol to get to moles. And then go ahead and divide moles by your solution volume. And actually these, I all refer to, 34 I all refer to 33. So, should be fine. All right. We won't get to the next assignment slide, but we are going to go forward a few more slides. They'll leave all sorts of problems for you guys to do over the weekend. So the two ways we talked about describing how concentrated solution is just now is grams of solute per liter of solution, moles of solute per liter of solution, but I would argue that the third way of saying how concentrated solution is weight percent. And weight percent or mass fraction. Let's see, have we talked about this? Yeah. So just to kind of remind you what that looks like, basically, if you are given the mass fraction, I think we did, when we talked about percent, we talked about mass fraction too. Basically, that is the grams of solute in 1 gram of solution. It's like a mass basis. Grams of solute in 1 gram of solution. Which would be what? Temperature independent, wouldn't it? That's a possibility. That is mass fraction. Okay. Mass percent, of course, is grams of solute in 100 grams of solution. Basically, you just scale it up 100. So we can use our concentrations to actually as conversion factors. So one of the things I'm going to emphasize, you see that G/L, one of the things I'm going to emphasize is you're going to have to unpack that to work a factor label problem. And I think I unpack it on the next slide, but G/L is grams of solute, in this case NaCl. L stands for then liters of solution. So you're going to have to unpack that. My suggestion to work problems like this sometimes is to pull out what you know. So let's see, what volume of solution, so question mark volume, solution. Sometimes it says what's the volume in milliliters or liters. But what volume of solution will contain 22.3 grams of NaCl? Okay, so I used that number. The number I didn't use is that number. So actually that concentration is going to be how we're going to go from grams of NaCl to volume of solution. So it looks like this. Unpack, this is what I mean. 14.3 G/L. I should never see you work a homework or an exam question where you just leave it G/L. Okay, that means grams of NaCl in this case per liter of solution. Okay, and of course the inverse is also a great way to think of the same solution. It's a physical property of the solution. And 1 liter of solution would contain 14.3 grams of NaCl. Sometimes I just kind of picture taking a liter of the solution, driving off all the water, and weighing back the residue. I'm like, it should be 14.3 grams. So let's work this problem. The first term is going to be the thing you want to convert. Okay, I usually put it over 1 though, so 22.3 grams NaCl over 1. And putting it over 1, you can clearly see that we need grams to cancel, be left with liters. So we're going to use the flipped version of the that particular concentration. 1 liter solution for 14.3 grams of NaCl. Units of grams of NaCl cancel. We're left with liters of solution. And as long as it didn't say volume in milliliters, you're done. So round to 3 sig figs, I got 1.56 liters of solution. So it can be kind of a practical thing. Okay, let's just say that you need in your vat, your reaction vat, you need 22.3 grams of NaCl. You know the grams per liter of NaCl in your solution, but all you can do is volume. So that's the volume you need to measure out in order to get that mass. That's it. Let's do another one. Okay, it looks a little wordier. Okay, I kind of start from the back sometimes. How many milliliters of the solution? So, question mark milliliters of solution. Okay. Should you use if you need 0.015 moles? Okay. Now, notice we're only dealing with one solution and one solute, so you need 0.015 moles of potassium dichromate. And then the only thing we didn't use is, dun, 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 molarity. So actually we're going to use molarity to get from moles of what our target solute is to volume of the solution we need to measure out. So again, I should never see a capital M for molarity when you work your problems. It should always be unpacked. So 0.255 molar means 0.255 moles of K2Cr2O7 per 1 liter of solution. Now, again, we're only dealing with one solute, K2Cr2O7. We don't have another species, so actually you could just do 0.255 moles per 1 liter. The inverse is also true about this solution. In 1 liter solution, it would contain 0.255 moles of K2Cr2O7. Here we go. So the first term is going to be the thing we want to convert. Every once in a while I'll have a student that will go with molarity first, and it works. But I would put that as the second term this time. So we're basically going from moles to volume. 0.015 moles or 0.015 moles K2Cr2O7 over 1. And I want moles to cancel, and so I'll use what? The flip version of the molarity. 1 liter solution per 0.255 moles of K2Cr2O7. So units of moles of K2Cr2O7 cancel. We're left with units of liter of solution. Oh, it wanted milliliters, didn't it? So we need one more thing. Yep. So one last term, we'll put 1,000 milliliters over 1 liter, and then we'll be done. So remember counting sig figs in that first term. And this term right here, of course, this one is not a significant figure, but neither is this one. So honestly, we are only allowed 2 significant figures. I hope that's what my solution has. 59 milliliters. So again, taking one last look at this, basically that's the volume you need to measure out in order to get 0.015 moles of the solute given that molarity. One more, or another one. I have several little ones, and then, okay. So let's go ahead and diagram this one. How many moles? Question mark moles. Are there in 75.0 milliliters, okay, of a solution that has this concentration? Oops. There's going to be one step in between here. So I'm going to diagram this coming up even better. That's kind of what we have going on. So we need to unpack that 0.108, and instead of having a separate slide, this is unpacking that 0.108 molar. So 0.108 molar CaCl2 means 0.108 moles of CaCl2, calcium chloride, per 1 liter of solution. So that's going to be how we're going to get from volume to moles. So now I kind of have the flow chart thing going, okay? We're going to have to first convert to liters, okay? We were given milliliters, so we're going to have to go to liters. And the reason we need to go to units of volume for liters is because that's what our molarity is in moles per liter, so we can't use it right away. And then we can go from liters of solution to actually moles using the molarity. So that's kind of that flow chart, the flow of that problem. So here we go. So I would start with the milliliters. I would put this over 1, 75.0 milliliters of solution over 1. Then I want to get to liters, so I'm going to have to put 1 liter over 1,000 milliliters. Then once I have liters of solution, I can go ahead and stick in molarity. And actually I'm going to stick in the non-flipped version because I want liters to cancel. So I'm going to put 0.108 moles of CaCl2 per liter of solution. Now units of liters of solution have canceled, and it looks like we're done. 3 significant figures, look right? Okay. So to give it 3 significant figures, this is a case where we need to actually use a trailing 0 after the decimal. So it's 0.00810. So of course, these are not significant, they're placeholders, okay? Significant, significant, and this is actually significant because it's a trailing 0 after decimal. And I have run out of steam. So that's a good place to stop, and we'll pick up there on Friday.